Yeah, excellent. Yeah, thank you all for joining. Yes, of course. Thanks, Natalia. We'll introduce our speaker. So thanks, Sleiman, for extending the invitation. We're honored to have you here. So a brief bio. Sleiman is that Dr. Sleiman Mhanna received his PhD in electrical engineering from the University of Sydney in 2016. For the subsequent 3 years, he was a research fellow at the same institution, working mainly on the consort project funded by ARENA. During that time, his research consisted mainly of fast distributed optimization methods, targeting a wide spectrum of applications in power systems engineering. Part of his research also revolved around designing nonlinear pricing structures for load-side distribution network support. In 2019, he was offered a senior researcher position at the University of Melbourne to work on future fuels CRC's integrated energy systems project, which mainly consists of developing an integrated electricity gas hydrogen system model to be used in analyzing different case studies on the potential of different future fuel options and technologies to decarbonize the existing energy system. The need for solving the resulting complex integrated model accurately and efficiently led him to develop novel sequential linearization techniques and advanced heuristics for tackling discrete decision variables. So thanks very much, Sleiman. You can start your presentation whenever you want.
Yeah, thanks, Elias, for the kind introduction. And thanks everyone for tuning in this morning. It's night here in Australia, but
yeah, thanks also for making it at 9 p.m.
That's fine. I mean, no one here goes to sleep at 9, so
it's summer.
So life of a researcher.
Yeah.
All right. So today I'm going to introduce to you guys a new class of iterative LP-based algorithms that are designed specifically for applications in electricity and gas systems. Today we're going to talk about the multi-period electricity and gas flow problem, which is one application in electricity and gas systems. So I will start by identifying how the physics of electricity and gas flow in multi-energy systems translates to difficult to solve optimization problems. I'll then talk about how they are addressed in practice, and after that I'll introduce sequential linear programming, which is the central theme of this talk. And finally I'll talk about how we have used this new class of SLP algorithms to solve difficult problems in electricity and gas systems, such as the optimal multi-period electricity and gas flow problem. So if you're trying to optimize the operation of electricity or gas systems, you will be confronted with a set of complicating non-convexities that arise primarily from the physics of electricity and gas flows. So in electricity networks, for example, non-convexity is mainly attributed to the definition of complex power, if we're talking about high voltage AC transmission. So in the definition of this the complex power, we have in which the product of the voltage and the conjugate of the current gives rise to non-convex quadratic equality constraints, as you can see here. That's of course after reformulation. We'll see shortly how we get to that point. In gas networks, on the other hand, non-convexity stems primarily from the discretization of the partial differential equations describing the motion of gas in a pipe. So which also gives rise to non-convex quadratic equality constraints. And I should say, well, this is for one pipeline in which the direction of flow of gas is known. If you don't know the direction of flow, this will be different. You'll have an absolute value here. We'll see also shortly how this constraint can be written. Now, in practice, most electricity and gas market operators around the world, including the Australian energy market operator, they generate the operating and pricing schedules by simplifying these problems using LP approximations, linear programming approximations. Now, the reason for using LP is that it's faster and more reliable than its nonlinear programming counterpart. Now, however, this trade-off comes at the price of one, higher operating costs in general, and of course higher CO2 emissions. Now, in the near future, when green hydrogen production and injection becomes reality, which is another topic that we're working on at the moment. Now, under these new circumstances, those LP approximations will not be able to price and track hydrogen across the gas network, which is a problem that is really a hot topic at the moment. Not sure if you guys are familiar with these new topics. So the central idea of this work is to develop a novel algorithmic framework for multi-energy systems that simultaneously retains the exactness of nonlinear programming and the reliability of and computational efficiency, of course, of linear programming. So you want it to be reliable, fast, and if you can have it converge to accurate enough solutions, then that's also an added benefit. So the innovation and significance of this algorithmic framework lies in offering system operators the opportunity to keep using their existing LP solvers, but now with the added benefit of exactly capturing the nonlinearities of the original problem. So by doing so, electricity system operators, for example, will be able to obtain accurate locational marginal prices that reflect active and reactive power losses, and will also be able to price reactive power, which, you know, as we've seen in the previous slide, is beyond the capabilities of current electricity markets, as far as I know, of course. The method is, the algorithms will also unlock the ability to capture the couplings between electricity and gas networks, as well as the flexibility of the gas network by, you know, for example, capturing the line back, which is instrumental in assessing flexibility of the gas network, and also the flexibility of electricity system since the two are physically coupled. So I will talk about all that in more detail in a couple of slides. And finally, the SLP algorithm will be can be straightforwardly extended to applications requiring discrete decision variables, which can then be solved using powerful MILP solvers. So now, to refresh your memory, sequential linear programming, or SLP for short, is also known as the cutting plane method, and it consists of solving the original NLP problem by a sequence of LP problems. So at each iteration, or each one of those LP problems, at each iteration approximates all the nonlinear functions by their first order Taylor series expansion at a certain point. And the algorithm then terminates when a certain stopping criterion is met, usually the degree of constraint violation. So now, to better understand how our SLP algorithm works, I'll start by identifying the two types of nonconvexities or non-convex equality constraints that crop up in electricity and gas system applications in general. So the first type consists of equality constraints that become convex when the equality is relaxed into an inequality. And here are some examples of that. And for the keen-eyed ones among you, you can clearly associate those with the type of constraints that appear in electricity and gas systems. We'll actually shortly see how they relate to the ones in electricity and gas systems. So so this type 1 is that's what we call type 1 actually, and so the sets defined by those equality constraints have a special property, which is that all the points in the set lie on only one side of the tangent hyperplane at any point in the set. So in other words, any tangent hyperplane to the set does not cut into the interior of the set. So that's what this you know, that it was a bit of a mouthful, but that's actually what it means. So if you draw or draw the tangent hyperplane at any point in this type 1 set of non-convex constraints, that hyperplane will not cut into the interior. And this is an important property that we're going to leverage. We actually leverage in our SLP algorithm. So we'll see that in a bit. Now, the second type of non-convex constraints consists of equality constraints that remain non-convex when the equality is relaxed into an inequality. So for those sets, we can no longer guarantee that a tangent hyperplane at any point in that set, on that set basically will not cut into the interior of the set. So we've this, if you under this classification, you can identify two types of non-convex constraints, and that's what we've done here. And we're going to see how the SLP algorithm that we've developed leverages this basically these properties of these non-convex sets. So now, but first, let's take a quick look at the history of SLP. So the first SLP approach is attributed to Kelly in the 1960s, and this method is tailored to convex optimization problems, where the first order Taylor series approximations are supporting hyperplanes to the feasible set. That was in a bit more detail. You can also think of it as an iterative polyhedral approximation of that convex set. Now, as the title suggests, this early SLP method works only on convex problems. Now, fast forward 15 years, Zhang proposed a penalty SLP approach for general nonlinear programming problems, but now with a trust region strategy to control the step size and ensure convergence. So it's a different construction than the one proposed earlier by Kelly. So to ensure convergence here on general NLP problems that can be non-convex as well is the trust region method to control the step size, and we'll see that in an example shortly. So this approach is actually the one that the solver Express SLP, FICO's Express SLP uses. I think it's straightforwardly based on Zhang's algorithm, that penalty algorithm, for those of you who are familiar with FICO's Express SLP. Now, the main drawback of this penalty SLP is that it needs somewhat extensive hyperparameter tuning to converge to acceptable accuracy. And more importantly, unlike we're going to see, unlike our SLP approach, this approach does not differentiate between the two types of non-convex constraints we saw earlier, type 1 and type 2. So this brings me to our approach, which is tailored to type 1 constraints. And as we said earlier, there are a special class of constraints, non-convex constraints, with the property that any first order Taylor series approximation is a supporting hyperplane to the feasible set defined by those constraints. So in a bit more detail, the method actually we proposed consists of a sequence of carefully constructed supporting hyperplanes and half spaces, and can be thought of as a hybrid between Kelly's method and Zhang's penalty SLP method. Now, of course, you can, if you're interested, you can refer to our these two papers here that we've published 6 months ago. And so now I'll use this small two-dimensional non-convex problem to demonstrate how these two SLP methods work, ours and the earlier one from 1985, and also underscore the main differences between them. So this small problem here you can see has a linear objective function and one non-convex quadratic equality constraint. And the optimal solution of the problem is shown here at that point. Now, the classical SLP, which is actually what FICO Express uses, starts by replacing the non-convex constraint, g of x in this case, by its first order Taylor series approximation, as shown here in red. And the trust region strategy is captured by this constraint here, which is basically linear, but we'll see what this does as you iterate through the sort of algorithm. Now, you can think of it, the trust region can be thought of as a contraction of the feasible space just to prevent the first order approximation from bouncing around too much. So without this, you'll probably bounce around from one point to another and never converge. So this is actually very important, crucial for convergence. Of course, you need to tune alpha, and you can imagine for larger problems you need a parameter alpha for each one of those variables. Yeah, it can be daunting for large problems, to tune this parameter. And now finally, R1 and R2, these are non-negative auxiliary variables used to that are used to prevent infeasible LP problems. But this, I mean, to make things easier, I could have written 0 here and should have been fine. But in general, these are needed. Otherwise, you may at the start of the algorithm you may have infeasible LP problems. So let's see how it works.
Sleiman,
Yeah.
sorry. Just a
No,
question.
please.
Maybe you'll explain later, but how do you tune? Is there like a way, or you try different values? Is there a method?
Now, of course, it depends. The best way to do this is to whatever problem you're dealing with, the problem at hand is you can sort of use the structure of the problem to have sort of like a informed guess of what these parameters can be. So it's yes, it involves a little bit of trial and error, of course. But now if you actually there is a somewhat principled way to do this. If you want to stick to classic textbook methods, you can refer to Zhang's method actually from 1985, and in there they actually talk about in detail how to tune these alphas. But of course, depends on the problem at hand. At the end of the day, yes, sure, you can follow the theoretical sort of concepts that are developed here, but
I understand.
in my opinion, it's you can gain better understanding if you use the structure of the problem at hand.
Yes. Okay. Yeah.
Now, so yeah, let's see how it works, iteration by iteration. Starting from let's assume we start from point. So I need a starting point, of course, because it's just like any other NLP. Let's say we start from x1 equals to 2, for example. We've got 2 variables, so x1 and x2 here. So in the first iteration, we linearize g of x around x1 equals to 2. Straightforward here, and we solve the LP problem. That's the LP problem shown here, and that's the graphical representation. So you solve that, and then you get the new point, the new iterate, which is x1 equals 0.5 in this case. So what do? Next, you simply at iteration 2, we linearize again around that new point, x1 equals 0.5, and we solve the new LP problem, which is shown here, to obtain the new point. In this case, x1 equals 1.4, and you can see it's a bit closer to the optimum that we identified earlier. Notice how the trust region constraints actually contract the feasible space. So these are the trust region basically constraints, and you can see how they contract the feasible space. Starting from here, for example, they were wider, and now they're contracting further, and of course they're captured by these linear constraints here. And then if you keep iterating, you can also see how the trust region is shrinking. And you repeat the same process basically at each iteration until, and of course at the same time shrinking the feasible space. And then so here, by the way, if you're interested, since Ilyas, you've asked me about how the parameter alpha, I'm simply dividing. The one heuristic is to simply divide the initial step that you took here, just divide it by 2 every time. That's one, of course it works for small problems, but for big ones, for larger problems, it may be problematic. But that's just one way to do it, just very very quickly, if I may say. But this is not really our approach. This is the classical method. This is how it works. I'm outlining how it works, the classical one, so that you can get a feel of how the new one works and get a sense of how different they are. So yeah, you keep, like I said, you keep iterating until eventually you converge to an acceptable or sufficient accuracy. In this case, of course, it's the same solution as we've identified earlier. So that's the classical SLP in a nutshell, basically, by Zhang in 1985, and that's the same one used in the state-of-the-art SLP Express Solver. Some of you might be familiar with that. So now let's have a look at how our SLP approach works. So if you look closely at this constraint, the quadratic constraint, you can see that it's actually of type 1. And why? It's because when you relax it into an inequality constraint, it becomes convex. Of course, I mean, why? We can go into details. The Hessian is positive semi-definite, or positive definite in this case. But I'm assuming most of you are familiar with convexity concepts. So type 1 means we can sort of leverage the supporting hyperplane theorem, as we've seen in a couple of slides earlier. So the key idea behind our SLP algorithm, shown here on the right, is to not only linearize the equality constraint around the point xk, like the classical SLP approach, but to also keep all the previous tangent hyperplanes from 1, so iteration 1 to iteration k minus 1, right? Now, of course, you don't, in practice, you don't have to keep all of them. There are ways to remove inactive ones, but I'm not going to go into the details. If you're interested, you can have a look at the papers. So those ones now become, the previous half spaces become inequality constraints. So it's so that's how you sort of approximate the iteratively approximate the sort of the feasible non-convex region. So now, because again, because it's a type 1 constraint, the linear equality constraint in red here is a supporting hyperplane to the set, just to be finicky or pedantic with the semantics, and the linear inequality constraints in green are supporting half spaces to the set. So none of those will actually cut into the interior of the set. So that's the beauty of this algorithm. Now, the first iteration is very similar to the classical SLP approach. This is actually the same as the SLP approach, minus 1 auxiliary variable, which I won't go into the details. Actually, it uses less auxiliary variables here because of that structure. And so now, at the second iteration, we notice that we keep the tangent hyperplane from the previous iteration. So that's actually how it works. So we kept that previous one, but now as an inequality constraint or a half space, as shown here. So the green constraint is the one shown here graphically. So now, yeah, we keep iterating and adding the tangent hyperplanes from previous iterations, and until we converge basically to a feasible solution. In this case, optimal, luckily. And that's the main part of our SLP algorithm in a nutshell. So in case you're wondering, R is again a positive slack variable that we use here to avoid infeasible LP problems, especially at the start of the algorithm. So that's basically how our method works in comparison to the classical one. So now so now that we know how to handle those nonconvexities, let's have a look at the multi-period optimal electricity and gas flow problem, which is an operational problem that consists of finding the least cost dispatch of electricity from generators and gas from gas supplies to satisfy both electrical and gas demands at all buses in the electrical network, and of course nodes on the gas network. And of course, this problem is subject to technical constraints and the physics of electricity and gas flow, like the AC power flow, of course, and the gas flow hydraulics and pipelines. In this case, quasi-dynamic gas flow. So the non-convexities are, as you may have guessed, the AC power flow constraints and the gas pipeline hydraulics, or the discretization of the equation of motion, which is basically this one. So in a bit more detail, these are the non-convexities fleshed out, basically. The AC power flow constraints on the electricity network side. Now, with a bit of reformulation, you end up with quadratic constraints here, or rotated second order cone constraints, and those are of type 1 actually, because if you relax that into an inequality, this becomes convex. Now, the cycle constraint here is type 2 because, well, if you relax that, it'll stay non-convex. So that's type 2, and we know how to handle that. Though we can use a hybrid algorithm basically to deal with each one of these constraints, each one of these 2 types of constraints. Now, Now, to make matters worse, the operation of bidirectional non-pipe elements such as compressors and pressure regulators requires the use of binary variables captured here with the Z variables, which means that we're dealing with an NP-hard MINLP problem, mixed integer nonlinear programming problem that has, and this MINLP actually has a non-convex continuous relaxation, which means that it's much more challenging to solve than compared to convex MINLPs which have a convex continuous relaxation when you relax the integer variables. So we will see shortly that a problem like that is intractable on real networks if we use MINLP solvers directly. On the other hand, SLP algorithm that we've developed actually can solve this problem extremely fast. So yeah, we tested this SLP algorithm on the real electricity and gas transmission systems of the state of Victoria in Australia, and we used actual line pack and demand profiles obtained from the Australian energy market operator. So that's the electricity network of the state of Victoria in more detail, which is of course coupled to the gas network physically through gas powered generators, of course. And this is the gas network, which we actually developed from scratch as part of this work. And you can see that we've got these compressors and regulators, both of which require disjunctive or disjoint sets to capture their operation. So in the numerical evaluation, we used Gurobi, solver Gurobi for the LP problems, and Juniper for the original MINLP. So Juniper is a Julia-based open source nonlinear branch and bound solver for those of you who are not familiar with Juniper. So Juniper is similar to Bonmin and Nitro, basically. For those of you who are familiar with Nitro and Bonmin. So from the table here, you can see that Juniper does not converge at all on the Victorian test system, whereas the SLP algorithm converges in less than a minute to a near optimal solution, as you can see here with the optimality gap here. So we're dealing. So remember that we're solving a joint electricity and gas operational problem over 24 hours here. So we're dealing with the large scale mathematical optimization problem. So now, of course, yes, let's talk about feasibility now. From the figure on the bottom, we can see that the SLP approach converges to a feasible solution with a maximum constraint violation of, in this case, well, it was at most 10 to the power minus 4, which is more than enough for practical applications. And you can find, of course, more results and studies in the paper. So yeah, finally, in order to validate the solution from a physical gas network standpoint, we back tested it against an actual 24-hour total line pack profile for a high gas demand day in Victoria. And you can see from the figure that the SLP solution very accurately predicts the actual line pack for that day. Now remember, the actual line pack was not a result of optimization, but yet the optimization algorithm is able to predict exactly very, very closely how the line pack changed that day. So this is how actually we gain confidence in both the modeling and and the representation of the gas network of Victoria, because this stuff didn't exist. Basically, this did not exist on. We developed that from scratch. So yeah, all right. Let's wrap up. So we numerically demonstrated that the SLP approach can converge to high quality and feasible solutions in computational times that are conducive for operational requirements of electricity and gas markets. We've also validated the SLP solution on the gas network model of Victoria using line pack backtesting with actual data. And yeah, finally, we're currently working on extending this SLP algorithm to the integrated operation of electricity, gas, and hydrogen systems. So now we're looking into blending hydrogen into existing gas networks and in the transient domain, which is a very difficult problem to solve. We actually have a paper accepted in Power Systems Computations Conference, PSTC 2022, and it talks about that exactly. And we use SLP here to solve the problem yet again. So yeah, go check it out when it's publicly available if you're interested. And in parallel, we'll also be extending the modeling and studies to the whole east coast of Australia, the electricity and gas networks of Australia. So so that's our plan for the near future. So I guess I'm on track with time. I guess took about 30 minutes. And that's it for me. Thanks guys. Thank you for tuning in today, and happy to answer your questions if you have any.
Yeah, that's excellent. Thank you very much, Sleiman. I'll just stop recording now and we can
Sure.